This is a video to summarize the equations for chapter 15 of the textbook on mechanical waves. Basically, all of the waves that we're talking about in this chapter will be on a string, which means they will be transverse waves, and you will have watched videos about the definition of transverse and longitudinal waves. So the first equation that's a super important equation is simply the velocity is wavelength times frequency. This is also equal to the wavelength divided by the period, which is also equal to the angular frequency divided by the wave number. Now this K wave number, it's not the spring constant, so often I will call it kappa, but the K in this chapter, which is called the wave number, is 2 pi over the wavelength. And the angular frequency is 2 pi times the regular frequency, this being in hertz, and this being in rads per second, and they're related by 2 pi. Now, this is different than simple harmonic motion because now we have two possible equations that you could draw. You can either draw the displacement of the string as a function of time, or you can draw the displacement of the string as a function of position. So if you're going to do this one as a function of time, it means that you are looking at one place on this string. So X would be constant here. And you're simply looking at these. Now this is simple harmonic motion. You're looking at the motion of one point on the string going up and down and up and down and up and down in time. Whereas this would be like a snapshot. And so this would be, you just take a picture of the string at a particular instant in time, and then you move along and see where the different displacements of the string are. Okay, now if we want to somehow do this with 3 variables, obviously you can't do it on a 2D graph, but to sort of show what's happening in X, T, and Y, what you could do is you could go, okay, at a certain time, this is what the string looks like. So this would be at t equals 0. And then you could go, oh, a little bit later, it looks like this. And you just move it over. So this would be t later. So that would be kind of putting together both these top graphs into one graph. Okay, now somehow we have to quantify this with an equation. The equation that I like the best, y of x of t is equal to a sine kappa x minus omega t. Okay, it is a sinusoidal function. It depends on the wave number and the frequency. So it depends on the wavelength and the frequency. The negative means that it's going to the right, traveling to the right. If it was a positive sign, it'd be to the left. A is the amplitude. Independent of the motion, that's something that you just fix depending on how you're going to generate this wave. Okay, and y is the displacement of the particles of the string, particles. It depends where you are, and it depends what time you're looking at that location. Okay, so now on this equation sheet, you have all kinds of other variations. By simply using the definition of kappa and omega, you can come up with all those other definitions, but this is your go-to. I mean, any problem, you can always use this equation. Okay, now if you're specifically talking about waves on a string, the velocity of waves on a string depend on how tightly you pull the string, the tension of the string, and how thick the string is. So this F is the tension. I prefer to use F sub T, but your text just uses F, that's okay. That would be in newtons. And then this is the mass density, linear mass density. And so that's the mass per length. So basically that's how fat the string is. Okay, the next equation on your equation sheet has to do the power associated with these waves on a string. So the power, average power, and of course we know that waves have power. I mean, just think about a water wave crashing into the shore. An oscillating string certainly has power. It produces sound. That sound comes out, you can hear it. So the formula they've given you for power, this is specifically for a wave on a string, because you've got tension here. If this was some other kind of wave, like a water wave or a sound wave, obviously you wouldn't have tension. So another good way to write this for other waves is mu v, where v is the speed of the wave, omega squared a squared. So it depends on amplitude, frequency, angular frequency, velocity, and now that would be a string, linear mass density of the string. Next, we can go to the equation for intensity. So that's power, power in watts. But then we talk about the intensity, which is a power per area. So intensity I is equal to the power per area. Now, if a wave is spreading out spherically, like from a point source, then that area very often is 4 pi r squared, right? Surface area of a sphere. And so that's why the intensity is inversely proportional to the distance away. So if you're next to, say, a really loud noise, and you want the intensity to drop by half, you would only have to move √2r away. If you want it to drop by a factor of 4, you move 2 times further away. And so the equation that's intensity 1 is to intensity 2 as R2 is to R1 squared. Oops. Okay. The next couple of equations are for standing waves, and I've done a couple of videos explaining what standing waves are and what all these equations are. So you definitely want to see standing wave video that I've got linked on D2L under YouTube video links. So see standing waves video. It's got everything you need there. Okay, so that'll do it for this one.